Okay, let's start my talk. The title of my talk you can see on the whiteboard. Actually, half a year ago, I gave a talk at this seminar, if you remember, which was devoted to a question in which case the automorphism group of an algebraic variety is an algebraic group. And let me recall the main result from that talk concerning this question. So if X, suppose X is an algebraic variety, then there is a contravariant functor denoted by alt X, alt sub X, from schemes over the base field groups, which sends a scheme S to the group of automorphisms of the product scheme S cross X over S, which means that you consider automorphisms that cover the identity map on S. And how does such an automorphism look like? At least on the level of points, you can express this phi, this automorphism phi, as a map sending a point small s, comma small x, to a point again small s, comma some other point in x, depending both on s and this x. Let me denote it again by the same letter phi, by use of notation of x, comma of s, comma x. So actually, an automorphism of this product scheme over S is defined by this map phi. And this map phi, this one, can be considered as an algebraic family of automorphisms of X parameterized by points in S. So this group of relative automorphisms consists of algebraic families of automorphisms, by which I mean maps from S cross X to X, such that a map constructed from this phi in this way is indeed an automorphism of this product scheme. On the level of points, this means that for any given point in S, you have an automorphism of the fiber of X parameterized by this point. So F
family of automorphisms.
for given point, you have a single automorphism. Big phi of S, comma X is small phi sub S of X, where this small phi sub S is an automorphism of X depending on S, on the point of S. In this sense, this big phi is a family of automorphisms parameterized by this big S. But of course, if you consider schemes, it is not enough to consider them on the level of points. You have to consider the structure sheet and how it transforms sometimes. But this is just to show you the idea. So the main theorem
what do we get if we take S to be just a point?
Then we get a single automorphism. The main theorem, the theorem 1 of Matsumura and Oort, says that if X is complete, then this functor is representable by a group scheme
connected component.
Let me finish.
My sentence. This is from our young years. So.
Is representable group scheme. Let me denote it in the same way, out sub x, but now out is upright. Here out is fancy, and here out is like in the paper typeset. So what does it mean, representable? This basically means that any such algebraic family of automorphisms, or any such phi as before, there exists a unique morphism, say small phi, from S to this group scheme, such that this big phi is pulled back from some universal family of automorphisms parameterized by this guy via the map phi. That is, again, on the level of points, this means that for any S in big S, the respective automorphism phi sub S is nothing but the image of S under this map phi. But again, on the scheme level, it is more subtle. So you have first of all, this means that you have a universal family of this kind, parameterized by this scheme. And the universal family is a map from out sub x cross x to x, which is actually an action of this group scheme on x. And any other algebraic family is pulled back from this universal one by the base change. By a map from S to this out x, to that out x. And even more, this out x, this scheme out x, is a locally algebraic group. This means that its identity component is indeed an algebraic group, a true algebraic group. But there may be several components, and even not necessarily finitely many, even countably many, in fact. So the group of components, why not, of out x, which is by definition the quotient group schema, that is better to say, out x mod out x mod, is either finite, is discrete, and either finite or countable. And in the latter case, so if it is finite, then the whole scheme out x is an algebraic group in the usual sense. If it is countable, then of course not, because it is not Noetherian. But in this case, even worse things can happen. This countable group may be not finitely generated. There are examples. One of them is due to
I'm sorry, and for those who are very poor in categorical theory, am I right that just for complete X, we have that the natural component is an algebraic group, and there is some
discrete part? Yes, this is what I have said.
Well, but
it's better to say that in zero characteristic this is true, because in positive characteristic this connected group scheme may be not reduced.
Okay, in zero characteristic.
But in zero characteristic all group schemes are reduced, the theorem of Cartier, so it is just a usual algebraic.
And then there, by scheme, we mean very abstract scheme, not necessarily a theorem.
Here, yes, locally of it is actually locally of finite type. Locally of finite type. generally not material because this guy can be countable. So one of the examples is due to Lisotta of 2016, and the other one is a similar one is due to Dean and Olgizo, 2017. And this example, I guess, I explained to you half a year ago.
So if we want to get the automorphism group of X itself, so we need to take the...
It is just what I'm going to say in a minute. So let me first comment that in the case of projective X, if X is projective, not just complete, then this theorem was proved earlier by Grothendieck. Using Hilbert schemes. And this I explained to you half a year ago. It's at the first part of this talk. And also, since this group scheme represents this factor, it is a very strong statement. In particular, if you apply this statement to describe algebraic families of automorphisms over S, when S is the spectrum of the algebra of double numbers, then you get the description of the tangent space at the identity point, that is of the Lie algebra of this group scheme. And the Lie algebra is actually the space of global sections of the tangent sheaf over X. This is a formal consequence of this representability property. And also answering your question, what is just the automorphism group of X in an abstract sense, the group of all automorphisms of X? It is nothing but the set of all points of the scheme over the base field.
Rational points.
Rational points over the base field. This means rational points in this sense. By the way, let me impose some restrictions on the base field. I will assume that the base field is algebraically closed and of characteristic 0. As we all like, I hope. And in this case, as I said, the automorphism group of X is just the group of k rational points of this scheme. And since k is algebraically closed, we can identify these two objects in a sense. At least we know that a reduced scheme of locally finite type is determined by its set of rational points, of geometric points on the base field. It is algebraically closed. It is Hilbert's theorem, Annotация.
And let us take a projective line in this equality for Lie algebra.
This example will follow. Okay, so now I have recalled more or less the content of my talk half a year ago. And now let me turn to the second part, to today's material. There are some natural questions which arise from this theory. So I always assume that my X is complete. Let me assume, for the sequel of my talk, that X is complete, and very often it will be projective. So, what are natural questions which arise in this context? The first one is, okay, this guy is always an algebraic group. Which kind of an algebraic group is it? And the second question is, in which case this group, this algebraic group, is linear? In which cases well, maybe this second question as I formulated is already a part of the first one. But let me formulate the second question differently. In which case the whole automorphism group is an algebraic group?
Linear.
Not necessarily.
Sorry.
And this means exactly that the component group is finite. And these are the questions which I'm going to discuss today. So my main reference will be lecture notes of Michel Brion, at a summer school in Warsaw, 2018. Notes on automorphism groups of projective varieties.
And these questions have complete answers.
You can repeat your question after I finish my talk.
It's not so.
You shall see if the answers are complete or not.
And maybe one more question is when the automorphism group is connected, is it a reasonable question or it's a difficult question?
When it is connected? Well, you know, I think this question is somehow this question is about this discrete part. Yeah?
Yes, but
so how big it can be.
The second question is also about discrete part.
Right, but here you can give a general answer. If you can prove somehow that this guy is an algebraic group, which means a closed subgroup in some bigger algebraic group, for instance, then you don't care what exactly this group is. You always know that it is finite, just because it is an algebraic group. But to study it explicitly, in particular to answer whether it is trivial or not, you have to study this discrete part. I mean, for a given variety, maybe you can succeed, but in general, I don't think you have a reasonable general answer.
Okay.
Say for complete toric varieties, the answer is known when it is connected. But it shows that sometimes connected, sometimes
yeah. So some combinatorics of this variety should be involved.
But for other questions, the answer is the same. Sometimes it's algebraic, sometimes it's no.
No. The idea is to prove that for some wide classes of varieties.
Right. Not for specific varieties, but for some class. Right. By the way, these notes are available at Brion's web page. So if you want to go into details, you need to consult this website. Okay, so let me maybe start with examples. first one is automorphism of projective space. And of course, it is the projective linear group. I think you all know this, but let me recall the argument, because this argument applies in some other situations. So if you have an automorphism of the projective space, then this automorphism acts naturally on the Picard group. The Picard group of the projective space is Z, generated by the class of the hyperplane bundle, the minimal ample line bundle. And this generator is distinguished because the other generator, the opposite one, is not ample. And of course, ampleness should be preserved under automorphisms. If you pull back your line bundle via some automorphism, then of course the resulting line bundle will be also ample. So this means that this action actually is trivial. And if your automorphism preserves the class of a line bundle in the Picard group, it can be lifted to the total space of this line bundle. And therefore, it acts on the space of global sections of this line bundle. This is a vector space of dimension n+1, say V. And the projective space, our projective space, is recovered from this space of global sections as the projectivization of its dual. So this means that actually any automorphism of x comes from a linear automorphism of this one, of this space, doesn't matter. X is not x. Sorry. My projective space. X is my projective space.
But this is in a sense x, the variety which we are interested in.
This is x in general, but now it is a projective space. So we deduce that phi comes from GL of V, or GL of V star, doesn't matter. And this is exactly this statement. The next example which I want to consider is smooth projective curves. Now, the answer here depends on the genus of this curve. So if the genus, let me denote it by G, if the genus is 0, then x is a projective line. And we already know the answer. If G is 1, then x is an elliptic curve. In this case, the tangent bundle is trivial. And the global sections of this tangent bundle are just constant sections. Let me recall that this space is the Lie algebra of the automorphism group. So this means that the automorphism group of an elliptic curve is one-dimensional. And in particular, its identity component is a connected one-dimensional algebraic group. But we know such an algebraic group, such a connected algebraic group, which acts faithfully on the elliptic curve x. It is x itself. Because an elliptic curve is an algebraic group. There is a group law on the elliptic curve. And x acts on itself by translations. This is a faithful action. This group is connected, one-dimensional, and hence it has to coincide with the connected component of the automorphism, of the whole automorphism. So what about the whole automorphism? It is easy to understand that it is a semi-direct product of its identity component, x, and a subgroup of automorphisms preserving a fixed point. For this point, I can choose the origin, the identity element in the elliptic curve considered as an algebraic group. Let me denote this group of automorphisms preserving the origin by this subscript 0. It is well known that an automorphism of an elliptic curve or even of an Abelian variety preserving the origin is a group automorphism. So this group is actually the group of automorphisms of x as an algebraic group. As we already observed, it is discrete because the connected part is this, and actually it is very small. I should write it somewhere here. Indicate that these are group automorphisms. Almost in all cases, it is just a cyclic group of order 2, with only 2 exceptions. There is one exception in which it is a cyclic group of order 4, and another one in which it is a cyclic group of order 6. This holds for an elliptic curve given by the equation x cubed equals y square z plus x z square c. This is an equation of a cubic curve on a projective plane. In this case, and only in this case, the group of automorphisms preserving 0 is z4, and z6 happens for the Fermat curve given by the equation x cubed equals y cubed plus z cubed. So these are the only exceptions.
Maybe some comment. Certainly, in general, the component group is not contained as a finite subgroup in the automorphism.
Yes, but in this case,
this is the case because the connected components act simply transitively.
Right, exactly. You can move any point to any other point. Any automorphism can be moved by this group to an automorphism preserving a given point. Right.
And secondly, any group automorphisms preserve 0, but all automorphisms preserving 0 are group automorphisms. This is some non-trivial.
This is a non-trivial statement about one of basic statements about Abelian varieties, in particular about elliptic curves. Actually, you can guess what is the non-trivial automorphism here. Any guess?
Inversion.
The inversion, exactly, the inversion. The inversion always is present in this group. And if you mod out your curve by the inversion, maybe it is instructive to write it here. So if you consider the quotient curve x modulo the group generated by inversion, you get a projective line. and my initial curve x is a double cover, a ramified double cover of this projective line. Ramified exactly in 4 points, which correspond to elements of order 2 in this group. There are 4 elements of order 2, including the origin. So say this is the origin, and these are the other 3 elements of order 2, and their images are 4 points, 4 distinct points in the projective, on the projective line. We can put one of these points to, say, to infinity, another one to 0, the third one to 1 on the affine line, and the fourth one to some lambda on the affine line, and this lambda is the double ratio of these 4 points. And what inversion does, inversion interchanges the sheets of this double cover. This means that, of course, inversion generates a normal subgroup in this automorphism group. So the quotient of this group modulo inversion acts on this projective line. And therefore, it must permute these 4 points. So it is a finite group, not just discrete, but finite. And furthermore, it must permute these 4 points, preserving the infinity, because it is the image of the origin. Origin should be preserved. And these points, these 3 points, may be permuted. And this permutation should preserve the double ratio of these 4 points. So it cannot be any permutation of these 3 points. So it cannot be the whole group S3. It is smaller. And it turns out that for some special values of lambda, of this double ratio, it can be the permutation by Z2, and in other cases, in some other case, for some other case, special values of lambda, it can be a permutation by Z3, a cyclic permutation.
This is a quotient of what?
This is the quotient of my elliptic curve.
The quotient of elliptic curve by group of order 2 is an infinite group.
It is a projective line. Ah, you mean? Then I maybe didn't understand your question.
So this is an infinite group, and you
This is not a group. This is just a curve. This inversion acts on this big X as an automorphism of order 2, and you may take a quotient. This is again a curve. This projective line. This is a classical thing: the double cover of projective line by an elliptic curve.
But you said that some subgroup is normal, so we have.
Since this subgroup is normal in this group, it is obvious that inversion generates a normal subgroup. Then this group acts on this projective line. This reaction descends to this projective line. And it permutes these points, and in a very special way.
You explained that Z4, Z6
yes,
extension
exactly.
of this.
I explain why there are only a few exceptions. Only for few values of lambda, it may happen that the permutation of these points, that this group permutes these points as transposition of some 2 points. And for some other values of lambda, it can be a cyclic permutation.
And if we know images of these points, we know the whole automorphism of P1.
Yes, because if you know how these points are permuted, then what can happen? Well, first of all, if you fix a permutation of these points, you determine this automorphism on the projective line, right?
Okay.
And if you know how this automorphism acts on the projective line, you know how it acts above up to inversion, up to permutation of sheets. So this explains.
Maybe the very last comment. You know that there is a nice problem for first-year student. Find all groups which have trivial automorphism group. And the answer is very poor. Just trivial group and group of order 2. But we have huge groups which have only 2 automorphisms. Right? Or this is algebraic automorphism.
Well, why not? No, I mean, you are not quite right, because
this is algebraic
Yes. We consider the automorphism of this X as a group and as an algebraic variety. Algebraic group.
Maybe group theoretically they have more.
Yes. Group theoretically more, even for an elliptic curve, because basically you may consider any automorphism of the latest periods.
The whole automorphism group is infinite.
The whole, no, Ivan Vladimirovich asks about the group of automorphisms of X as an algebraic group.
Ah, yes. Okay.
Not as a variety, as an algebraic group. And it is this one. Okay? And finally, if the genus is bigger than 2, bigger than 1, at least 2, then in this case, the tangent bundle is anti-fold, so it has no sections. And this means that the automorphism group is discrete. And even more, in this case, the tangent bundle is anti-ample, but the cotangent bundle, the canonical bundle, is ample. Actually, the third pluricanonical map is an embedding. So the third power of the canonical bundle is very ample. So we have an embedding of these curves of genus bigger than 1 into the projective space, which is the projectivization of sections of the dual to sections of the third power of the canonical bundle. Actually, the third power you need only in the case of genus 2. In all other cases, you need even the second power for hyperelliptic curves, and for curves of general type, even the canonical bundle itself works. This is classical theory of algebraic curves. And this means, in particular, that the automorphism group of X is not just discrete, it is finite. It is an algebraic subgroup in the projective linear group of this projective space. It is a closed subgroup because it is identified in this projective linear group just as the group of all projective automorphisms preserving the image of X. It is a closed subgroup, it's easy to see. So it is even finite in this case. And maybe the last example.
It's interesting that there are restrictions on how big it may be.
The restrictions?
On how big it may be.
Oh, yes, actually, good question, thank you. The order of the automorphism group of a curve of genus at least 2 is at most this peculiar number 84 times g minus 1. And maybe the last example is Abelian varieties. This example generalizes the second example.
So your examples with curves shows that sometimes linear, sometimes not.
Even I can say more. My next example will show a bit more. My next example will show more. So consider now the case when X is an abelian variety. This example is very similar to the case of elliptic curves because an elliptic curve is the simplest case of an abelian variety. So in this case, the tangent bundle, it is of course no more a line bundle, it is a vector bundle, but it is trivial. The trivializing sections are invariant vector fields. This is the case for any Lie group actually. If you have a Lie group, then the tangent bundle of a Lie group is always trivial. You have invariant vector fields which trivialize the tangent bundle globally.
So you wrote 4. Number 4.
Number 4. Number 3. Sorry. didn't have number 4, number 3. So the tangent bundle is trivial. It is trivialized by invariant vector fields, and the space of invariant vector fields is exactly the Lie algebra of X. This means that the global sections of this vector bundle are only constant sections. It is exactly the invariant vector fields. Left or right doesn't matter because the group is commutative. So the connected automorphism group of an Abelian variety is a connected algebraic group with this Lie algebra. Of course, we know this group. This is X itself, again acting on itself by translations. In the same way as for elliptic curves. And again, in the same way as for elliptic curves, the whole automorphism group is the semi-direct product of its connected component and the group of automorphisms preserving the identity element, the zero of this Abelian variety. This group is discrete, but in this case it may be infinite. A simplest example is like this. Suppose my X is a product of two copies of another Abelian variety. Then I claim that the group automorphisms of X contains GL2 of Z. How GL2 of Z acts here? In a very simple way. You have a matrix, 2 by 2 matrix, invertible 2 by 2 matrix over integers, and you have a point in this X which I write as a column vector, y1, y2. And the action is in the usual way. So this point goes to A y1 plus b y2, c y1 plus d y2. This makes sense because the coefficients are integers and you have an addition operation on an Abelian variety. So this is just a multiple of y1 in y and so on.
And this is a group
Of course.
Do you have an example of a variety with a linear natural part and unfinitely
Infinitely. Well, well.
And with big component group.
Say you can take a trivial example. There are examples, and I gave one of them half a year ago, in which the automorphism group is discrete but countable. And you can multiply this surface. It was a surface by something else which has a positive dimensional linear automorphism group. So you may cook.
Okay.
Yeah. Actually, this is a good question because all these examples show how various can automorphism groups of projective varieties be. So they may be connected, like for Pn. Yeah. They may be disconnected, but linear algebraic. Maybe. Well, they may be even finite, and hence linear algebraic for trivial reasons, as for curves of genus bigger than 2. They may be algebraic groups, but not linear algebraic groups, as in the case of elliptic curves. And they may be not linear algebraic, as in the case of Abelian varieties. They may be not algebraic groups, even, as in the case of linear varieties. And the identity part may be not a linear algebraic group. So various things can happen. By the way, maybe it's a good point to state a general result of Brion. In fact, any connected algebraic group can appear as the identity component of the automorphism group of some algebraic variety. Let this be theorem 2. Any connected algebraic group G, either linear or not, doesn't matter, can appear as the identity component of the automorphism group for some smooth projective algebraic variety.
The component group is somehow don't depends on this part, so you.
Yeah, I don't think that there is a strong relation between the component group and the discrete part. More or less any pair.
Okay.
So if we erase the 0, this theorem is not true, yes? Not connected.
If we could, well, I don't know. Actually, I don't know.
Any finite group can realize it as an automorphous group of some strange curves.
Every finite. But this doesn't answer.
Yelonic.
This still doesn't answer.
Is it effect?
Yes, theorem by Yelonic.
This doesn't answer this question in affirmative, because the automorphic group of X itself may has constructed by Brion may have some discrete. Okay, so now I want to focus on a question when, so maybe that would be question 3. When the whole automorphism group of X, or at least its identity component, is a linear algebraic group. This is the type of topic, so now I come to this subject. And I'm going to give several positive results in this direction. But let me start with a negative result. If this group, the connected automorphism group, is, or even automorphism, doesn't matter, if it is positive dimensional and the variety X is not uniruled, then no chance. So the theorem says that if X is not uniruled, then the identity component of the automorphism group is an Abelian variety. Maybe trivial, maybe just a point, but it is an Abelian variety. The proof is very simple.
What is the meaning of this uniruled?
Huh?
What is the meaning of this?
Uniruled means that there is a rational curve passing through any general point. So this variety is covered by rational curves. This means uniruled. And actually, if general, then through any. This is not hard to prove. So uniruled varieties, if we speak about sociology of algebraic varieties, then uniruled varieties form a small part of algebraic varieties. General algebraic varieties are not uniruled. So in general, this automorphism group, or this one, has a chance to be linear algebraic if only if it is finite, trivial in this case. So what is the proof? denote this automorphism group, this connected automorphism group of X by G. If it is not an abelian variety, then it contains a normal affine subgroup. There are some structure theorems on algebraic groups. I guess that some time ago I gave a talk on this subject. And in particular, any connected algebraic group contains the largest connected normal affine algebraic subgroup, the affine part of G.
All your talks are connected.
This is because you invite me to speak on connected subjects. So this group is affine and non-trivial, affine or linear kind of method. Affine, non-trivial. And if you have such a group, then such a group contains a one-parameter subgroup, say H, which is either additive or multiplicative one-parameter group. And now if you take this H and apply this H to a general point in X, consider the orbit map, then the image is a rational curve. For general X. Some points X, of course, may be fixed, but if H is one-dimensional, then it acts faithfully on X, so there are non-fixed points. General points are not fixed. So we have contradiction. X becomes uniruled. Okay, so for uniruled varieties, nothing interesting will appear as if we study this question. But what about ruled varieties, uniruled varieties? What about uniruled varieties? Maybe the most interesting subclass of uniruled varieties is Fano varieties. For Fano varieties, we have a positive result. So the fourth theorem says that if X is Fano, then even the whole automorphism group of X is a linear algebraic group. How do you prove this? What does Fano mean? Fano means that the anti-canonical line bundle on X is ample. It's a smooth variety with ample anti-canonical bundle. And some power of this anti-canonical bundle is very ample, and we get an embedding of X into the projectivization of the space of sections of some power of the anti-canonical line bundle. And of course, since this line bundle and its power is canonical, all automorphisms of X act here. So if you have an automorphism of X, it acts on tangent bundle and it acts on its top edge power, which is the anti-canonical bundle. Also, it acts on any tensor power of the anti-canonical.
So this embedding is important to guarantee that the section is effective, right?
The section? Which section?
This action is effective
Well, the action is effective on X.
on X.
Yes. Yes, right. Because if you have an action of any line bundle, of automorphisms on any line bundle, then of course this group acts on sections, but this action may have kernel. Since X is embedded in here, then the action is effective. So this means, again, that the automorphism group of X is embedded in the projective linear group of this projective space. And embedded as a closed subgroup. Because again, the automorphisms of X are identified among all projective automorphisms of this projective space just as transformations preserving the image of X. This is a closed subgroup. So for Fano, everything is okay. Well, let me come again from one side to the other one, to the opposite one. Opposite to Fano is the class of varieties of general type. What is a variety of general type? It is a variety, a projective variety, for which the canonical bundle is big. Big means that it has, roughly speaking, it has many sections. So the next theorem, theorem 5, says that if the canonical class of X is big, let me explain what does it mean. This means that once you have a divisor, once you have a line bundle given by this divisor, you have a rational map from your variety to the projective space like this. So not necessarily embedding, even not necessarily a morphism, but in general a rational map. And bigness means, well, for this bundle, means that for some power of this bundle, for some multiple of this canonical divisor, this embedding will be birational. This map will be birational. This is bigness. And if the canonical class is big, then not even the automorphism group of X, but even the group of birational automorphisms of X is finite. Well, for some, I didn't write it here, for some, maybe sufficiently big. This is bigness. In this case, the group of birational automorphisms of X is finite. Well, the proof is more or less like here. You just replace the anti-canonical bundle with the canonical one. Let me say a few words. First of all, you may replace X by its image under this map. Which is the projectivization of the algebra of sections of all tensor powers of the canonical bundle. Symmetric the correct way. The symmetric algebra over the canonical bundle.
Should the symmetric be outside of H0?
No, symmetric algebra. So symmetric algebra of a line bundle means the direct sum of all its powers, of all line bundles like this. And the projectivization of this algebra, of this sheaf of this algebra, the projectivization of this algebra is the image of X under this birational map for any m. Well, maybe for m big enough. Anyway, the natural map from here to here is birational, and actually any birational automorphism of X acts on sections of any power of the canonical bundle. This is again a classical fact in algebraic geometry, because if you have a birational automorphism, it acts on differential forms, maybe turning them to differential forms not everywhere defined. But the indeterminacy locus will be of codimension at least 2. And on a smooth variety, this singularity can be eliminated. So we can look in Hartshorne's book and justify that there is an action of birational automorphisms of X on this algebraic variety, on this projective algebraic variety, by true morphisms. So here, the group of birational automorphisms X, and therefore, by this argument, it suffices to prove that the group of birational automorphisms of this guy is finite. Yeah? So we may replace
regular automorphisms.
Yes, you may reduce to regular automorphisms, first of all. So you may replace X with this variety and may assume that K sub X is very ample. And replace birational automorphisms with regular automorphisms. And in this case, the argument, well, maybe not very, just ample. Because Kx turns into the canonical hyperplane line bundle here. And in this situation, the argument is exactly as here. Just remove minus here, and everything repeats. The argument is like here. But what you get from this argument, you get that the automorphism group of X is a linear algebraic group, yeah, because it is a closed subgroup in Picard of X, linear algebraic. But we already know that if X is not uniruled and varieties of general type are not uniruled, then the identity component should be an Abelian variety. Both linear algebraic and Abelian variety means trivial. X not uniruled implies that the identity component is trivial. And the whole automorphism group is therefore finite. This is the proof.
How do you replace birational with regular?
Because the group I am interested in acts here by regular automorphisms already. And now I just deal with this variety and with regular automorphisms of this variety.
Well, to the theorem 4, actually we can generalize a little. We can say that if we have an ample bundle and the whole automorphism group acts on it, then we can say that.
Right, but how you can guarantee that such an ample bundle exists?
Well,
by the way, in some situations, this is a method to prove that the automorphism group is linear algebraic. And
also, I would like to note that this result shows that there are fields which are finitely generated extensions of our ground field with finite automorphism group. This is strange. Algebras may have finite automorphism group, but fields?
Fields are finite automorphism groups over the base field.
Over the base field. We consider only automorphisms which are identical.
Birational groups of birational automorphisms may be small. this happens. Okay. Now let me turn to some other conditions which guarantee that either the identity component or the whole automorphism group is linear algebraic. So first of all, let me observe that the Picard group of my complete variety X also has a structure of a locally algebraic group. Its connected component, Pic not of X, is some connected algebraic group. And the quotient group is discrete, and it is actually finitely generated. It is known as the Néron-Severi group. It is a finitely generated Abelian group. If X is normal, then the identity component of the Picard group is an Abelian variety. But if X is not normal, then this group may be a linear algebraic group, for instance. For instance, if you take a plane cubic curve with a cusp, then this Pic not X will be the additive one-parameter group. And if you take a nodal curve on a plane, on a projective plane, then this group will be a multiplicative one-parameter group.
Just a moment. For rational varieties, this group is trivial.
For normal rational varieties, yes. But the nodal curve of the caspidal curve is not a normal variety. For normal varieties, yes, I mean variety, and if it is for rational, yeah, for rational varieties, for rational varieties, yes. In general, it may be big. It is what is called a Picard variety of X.
It is Abelian variety has a name.
Yes, it is a Picard variety. Yeah. So the next theorem. Theorem 5. It's theorem 5, 6? 6. Theorem 6 says that if X is projective, and the Picard variety is trivial, so the Picard group is discrete, then the connected automorphism group is a linear algebraic group. Prove it, or this sketch. So first of all, observe that the automorphism group of X acts and this Picard group, and this action is an algebraic action. In particular, the identity component acts at this group as an algebraic group, as a connected algebraic group. But this group is discrete. This variety is discrete. The whole Picard group is a discrete scheme. So the action is trivial. The connected automorphism group acts on the Picard group of X trivially. Now let me take a very ample line bundle. L over X. And since this group acts on Picard trivially, it preserves the class of this bundle. So every automorphism in this connected component of the whole automorphism groups, whole automorphism group preserves the class of this line bundle in the Picard group. And this means that this automorphism lifts to some automorphism of the total space of this bundle. So this total space is some variety fibered over X with fibers which are one-dimensional vector spaces, so affine lines. We can projectivize, we can take a projective closure. So I consider the projective closure of the total space of this line bundle, which is just the projectivization over X of the direct sum, L plus the trivial line bundle. And how does this variety look like? So you have X, you have a line bundle over X, this L. You have a zero section for this line bundle, which is a copy of X embedded in the total space of L. Let me denote this zero section as L sub naught. And since you take a projective closure, you already have a section at infinity. Another copy of X, which is obtained by adding a point at infinity on each affine line to each fiber. So each fiber is P1. This is, say, 0 on this P1. And this is infinity on this P1. So you have a projective bundle, and you have two sections of this projective bundle. Now, the automorphism of this L bar, so the automorphism of L covering the automorphism of X, which I consider, preserves the fibers and acts on fibers linearly. So this automorphism extends to an automorphism of L bar. And this automorphism of L bar, again, preserves the fibers and fixes points here and here. So it fixes these two sections, L naught and L infinity, pointwise. All such automorphisms form a group, and we get an exact sequence of groups. Like this. So you have the group out of X. You have a subgroup in out of X consisting of automorphisms preserving the class of L in the Picard group. The stabilizer of the class of L in the Picard group. And as I already observed, this group contains the automorphism, the identity component of the whole automorphism. And any automorphism from here lifts to this guy as an automorphism permuting fibers and actually commuting with the C star action on each fiber. Yeah? And preserving the sections at 0 and at infinity. Let me denote this covering group somehow like out of L bar, commuting with GM, with the multiplicative group on fibers, and preserving the sections L naught and L infinity. So this notation is somehow self-explaining, I hope. This is the lifting group. Sometimes this group is called the lifting group for this group. And the kernel, so there is a natural map, descent map, and the kernel is the group of automorphisms preserving fibers, acting on each fiber, preserving these 2 points. This is just C star, the multiplicative group. we have such an exact sequence. And observe that this group already acts in the space of sections of my line 1 group, because it acts in the total space, yeah, by fibrous linear transformations. It acts on the space of sections. And therefore, we get a map from this group to the projective linear group of this space, because this group acts on this vector space, but the dilations act trivially here, of course. This group acts here by dilations, and it acts trivially on the projective space. So if you want to consider transformations of the projective space associated with this vector space, then you have to mop out this group. So this group maps to PGL of this vector space, or of a projectivized vector space, doesn't matter. PGL of H0 X L, maybe I could start here. And this actually is an embedding. This map is an embedding because L is very ample. And again, X embeds as a projective subvariety in the projectivization of this vector space, dual to the space of sections of L. So again, as we already seen in some proofs before, this group embeds in this projective linear group as a closed algebraic subgroup, and therefore it is an algebraic group, and therefore this one also is a linear algebraic. Of this stabilizer of the class and the connected automorphism group of X are linear algebraic. So this is yet another good situation. Projective varieties with discrete Picard group. For instance, toric varieties.
Inductional rational.
Rational varieties, yeah. But this statement is just about the identity component. The next statement, and this is maybe less known, this is a theorem of Brion, is about the whole automorphism. And this is the last theorem in my talk, so I will finish very soon, just be patient.
But this is not a criterion.
No. All these theorems are just one direction. Almost all these
Because
theorems.
for generic varieties, the automorphism group is trivial.
Not only
Okay,
because of that.
and what?
Not only because of that, but just because indeed there are no criteria. There are some necessary conditions, some sufficient conditions for automorphism group to be linear algebraic, but not at the criteria.
No, but this is that for wide classes we have this.
Yes. And this is good because these classes cover many varieties which we like. Many varieties with rich automorphism groups which we like to study. So the last theorem by Brion.
Are there any conjectures or criteria?
I don't think so. At least I didn't find any kind of such conjecture in Brion's notes.
They should include typical varieties.
No, for typical everything is clear. For typical.
No, but if it will be a conjecture, this group
This
is linear
conjecture-
algebraic if and only if some condition.
Yeah. I
This
mean-
condition should include typical varieties.
No. Maybe the condition may be some cases. In this case, this condition. In that case, another condition. So you may imagine something like this, but nothing of that kind is known so far. So what is this theorem? This is the theorem of Brion of 2008. Yes, 2018. If X is normal projective variety, And if there is an action of a connected linear algebraic group on X, so G is a linear algebraic group, connected linear algebraic group, connected linear algebraic group, such that there is an open orbit with open orbit, just with open dense orbit. Then the whole automorphism group of X is a linear algebra. So this applies to several nice situations which we like, for instance, to spherical varieties, projective normal-spherical varieties, to toric varieties again, projective normal-toric varieties, and other cases. So this is a nice result, and maybe I have some time not to prove it in detail, of course, but to sketch a proof. Let me try to do it. This will be the end of my talk.
But of course, this group may be bigger than they can
Than G.
Than G.
Of course. It may be bigger than G even in its identity component, and even more with other components. So sketch of the proof. First of all, observe that, well, let me denote the open orbit of this G in X by X naught. It is an algebraic homogeneous space, isomorphic G mod H, where H is a stabilizer of the base point. So this is an open orbit. Since G is a linear algebraic group, it is a rational variety. We have the orbit map, surjective orbit map from G to this X naught, and G is a rational variety. And therefore, X naught and X, of course, is unirational. Now, a lemma, which was already mentioned several times by Dmitry, says that if X is a unirational variety, then the Picard group of S is discrete. So the identity, the Picard variety is true. Why so? Otherwise, since we assume that X is normal, otherwise this Picard variety is a positive dimensional Abelian variety. Yeah? So otherwise, this guy is some positive dimensional Abelian variety. And this Abelian variety parameterizes continuous families of line bundles over X. Yeah? So there is a universal line bundle which represents all these line bundles. So we have a universal line bundle. Say L over X cross A, such that when we fix a point in A, you get one of line bundles over X which are parameterized by points of this guy. So you may imagine such kind of picture. So you have X, you have A, you have the product, and you you have this line bundle over the product. Okay? Now, since you have this map from G to X, you may consider so this map from G to X induces how to say no. Let's go a bit differently. So you have this universal line bundle, yeah, and this gives you a map from X to the Picard group of A. You just take a point in X and consider the fiber over this point under this projection and restrict your universal line bundle on this fiber. You get a line bundle on A. So you have a map from here to here. And also you have a map, and this map is non-trivial. Non-trivial, because if it is trivial, if all these line bundles restricted to fibers, isomorphic to A, if all these line bundles are isomorphic to each other, then actually they give you one and the same family of line bundles over X. Because you may twist by the inverse of this line bundle of A, this universal family. And this doesn't change line bundles on the horizontal fibers, this twisting. So if you twist by a line bundle on L, then the line bundles of the horizontal fibers of this cross product will be the same. So if all line bundles of vertical fibers are isomorphic, then when you twist, they become trivial. And this means that on horizontal fibers, all line bundles are isomorphic. But A parameterizes all line bundles on X. Since this parameter space is positive dimension, it cannot happen that all line bundles on horizontal fibers are isomorphic. So this explains why this map is non-trivial. It is on one side. But on the other side, you have this map from G to X. And G is rational. So the map from here to here is a map from a rational variety to the Picard group of an Abelian variety. But to the Picard variety, yeah? To the Picard variety of an Abelian variety. Because X is connected, and so we get into here. And this is again an Abelian variety. This is an Abelian variety due to this A, actually. And an Abelian variety does not contain rational curves. Contains no rational curves. But here there are plenty of rational curves. G is covered by rational curves. So this map turns to be trivial. But this cannot happen because both these maps are dominant. Well, this map is dominant and this is non-trivial. So this is a contradiction. Okay, so the Picard group is discrete.
But this is a difficult argument for unirational. For rational, this is obvious. Because for rational, you have an open subset which is isomorphic to open subset of a affine space. And any divisor will
yes,
say
you're right.
You're right.
But here we cannot get irrational.
Yes, yes.
In the same. And now, since we know that the Picard group is discrete, the previous theorem applies. By the previous theorem, theorem 6, implies that the identity component of the automorphism group is linear algebraic. So we only have to deal with other components. I think that I have no time to continue. Maybe I shall stop here. The argument the rest of the argument is not long, but anyway it requires some technical considerations which I anyway supposed to omit, so maybe I just stop here.
I have a comment, because we have theorem number 8, which is not covered by this. Namely, we proved 4 years before Brion, this house in Herpik and Brion.
By the way, excuse me, I interrupt you. Let me comment that before Brion. Let me comment that this theorem was previously proved by whom? By Fu and Zhang in 2013 over complex numbers. In analytic setting. So X was supposed to be a Keller manifold. Not necessarily algebraic, not necessarily projective. And the same state. So smooth Keller manifold.
And
the
the
same
group
state.
of holomorphic.
Holomorphic automorphisms. Yeah.
We prove that if the Cox ring is finitely generated, then the group is linear algebraic. It also includes, as you say, rhetoric varieties, theoretical varieties, and so on. No group action is needed, only Moridian space condition, only finite generation.
Yeah, Moridian space, of course, also guarantees such kind of things because you reduce questions to the affine space, to some affine varieties. So you can deal with something linear, some linear groups acting on vector spaces. But I think that, well, I don't see maybe any obvious application of Brion's theorem beyond these nice classes of spherical varieties. But at least any quasi-homogeneous variety, there are plenty of them. So that is covered by this theorem.
Any more questions? If not, then in half a year we expect next connected talk.
You should give me a topic. Like a little tragedies by Pushkin. Give me a topic.
Okay, so this is all for today. Thank you very much. Next time we will have a talk by Timofey. This will be our experience with linear codes coming from toric varieties. Okay.